Welcome to Economics 410 Applied Regression. In this video, I'm going to talk about storing the fitted or predicted values in R. You're going to be able to save predicted or fitted values in a data set, and you're going to be able to use those new values for further analysis. So to start off here, I'm going to use a data set called UN11 that's available from Weisberg in a package called ALR4. So we'll install that package first. And then we're going to create a new data set, UN11A, just for the purpose of being able to work with it and modify it. That's not critical necessarily, but I'm just going to create a new data set, modify it. And then I'm going to build a model. So you see it there on the screen, hopefully, life expectancy for females as a function of fertility and the percent that live in urban areas from this data set. And the variables aren't important at the moment. We just want to get familiar with this process of having a model and getting the fitted values. And we're going to create a new object, m.fle. So M for model, FLE, female life expectancy, let's say, and that'll be for the estimated model. So then we're going to be able to store the fitted values. We're going to have a function here called fitted, and you see here, so we've got this fitted function on that object, and we'll just call it something like y hat, and we'll also be able to get the residuals with a function resid on that, and we can store that as something like res, for example. Those are some options for us there. All right, so here I am in R, and I have already installed this package up here. So ALR4, we've got the library that I've already read in. I clicked on the run button up here. So when I want to run something, I'll click on this run button typically. I already have no data over here. So in this window, you might be able to see that there's nothing there. So I've got that there. And so I'm going to start over here by creating this new data set, UN11A from UN11. And I'm going to have that in there, run that, and it creates it here. If I want to know more about it, down here, I can type in at the bottom, you see, I type in help, and I can put in UN11, hit enter, and it gives me more information about this data set. So then I want to create a model, and I'm going to just call it m.fle, for female life expectancy. That's what one of these variables is. So I'm just going to have that be a linear model of life expf. So we can see this over here, this variable down here, if we're looking over on the bottom right. And that's going to be a function of fertility and percent urban. And actually before that, I want to go ahead and do something up here. I'm going to attach this data set there. So I'm going to run that. So click run, and then I'm going to run the model. So then I want to go ahead and look at the coefficients. So I'm going to go ahead and look at those down here, coefficients and m.fle, and I'm going to click run, and it shows them to me down here. So the intercept on this model is 81.53. And then fertility, I can look over here. That says that's the number of children per woman. So more children, life expectancy goes down. PCT urban is percent urban population that lives in urban areas. So as that gets larger, life expectancy goes up. Okay. So then I want to get the fitted values. So let's see, fitted values. And what I'm going to do here then is I'm going to look at adding a new variable here. I'm just going to call it well, I'm going to say UN11 AY hat. And I'm going to have this be fitted or m.fle. I'm going to click run. So it creates those. And then I'm going to just compare here, and I'm going to create my own version of this. So I'm actually just going to copy this and I'm going to paste it in here, but I'm going to make a little change. I'm going to call this my. So I'm doing this outside of this black box, right? So using this fitted function here is a little bit black boxy, so to speak. And what I'm going to do here then is I'm going to create this based on the, I'm going to create my own based on these coefficients. So I'm just going to copy these from down here, the output. And I'm going to notice that this one is multiplied by fertility. So fertility there. And then add, this last one is multiplied by percent urban. Okay, so I'm going to do that. And it creates those there. Now what I'm going to have here then is I want to check and see whether or not what I did using the equation matches what R is doing with this black box function called fitted. So I'm going to go ahead and make another variable, 11a, and I'm going to call this D for the difference between the two. And so what I'm going to have here then is I'm going to take this y hat value that R gave me, put it in here, and I'm going to subtract the value that I found on my own. So my y hat, and I'm going to run that then. Okay, so now I've got this variable D here, and I want to check out what that does. So I can do a few different things to look at that, and I'm going to start off by just saying the sum of this value, this difference. I expect it to be 0 or very close to 0. If my values are the same and I'm subtracting them from the values that are constructed, I ought to get something very close to 0 here. And in fact, I do. So down here, I look at this. And what is this number? It's 0.00001. So it's not exactly 0, but there's some rounding in here, right? So when I use these values here, R is actually in the background has them taken out to even more decimal places. It's done some other things. So there are going to be some small differences there. I can also, though, construct a histogram. So I can look at this hist, and I can put in this variable here, this difference, and get that there, and run this out. And it creates a histogram for me over here. You'll notice, if we're looking at the histogram, so I'm looking over here, that these values are all very small, right? So 1E-07, 0 out here. So these are all, they're not all identical, but these are just the little rounding differences out at the 4th, 5th, 6th, 7th, 8th decimal place that are resulting in this slight difference here that you have. Okay, so I can also look at a few values here. So let me just check out a few of these values. I'm going to put in UN11A. I can check out some of these differences, D. And then what I'm going to have in here in these brackets is I'm going to tell it to give me observations 1 through 10. And that's just going to print out 10 values for me to look at. They should be very close to 0. And you'll notice they are, right? So this one down here is after 7 zeros, so decimal place, and then 7 zeros, then I get 1/6, right? E-8, so again, going out 7 decimal places, going out 7 decimal places. This one only go out 6, right? So this is a relatively large one here. It's 0.0000001, right? But that's still, I think, a fairly small number. Okay, so you can just get an idea there. There's some other things you can do to check this out, because I haven't proven that, that they're all 0, but you can see that they're all very small here. Looking at the histogram, they're all very small. All right, so another thing I want to do here then is I want to look at analysis of variance, or I'm going to look at an ANOVA table. So this is going to show the sum of squared residuals, right? So shows sum of squared errors or residuals. And this code is available to you in Canvas. I'll have a few modifications. I've got some different notes that I'll type in and get it cleaned up here. But you'll have this available to you in Canvas, or you do have it available to you in Canvas. And so what I'm going to do here then is I'm just type AOV, and I'm going to type m.FLE for this model, and let's see what that gives us here. So that gives us these sums of squares. So I can look at these values here, and those are the sums of squares errors here that we have for this one that says residuals. So this here is the sum of squares explained by fertility, using that as the first one. This is the sum of squared that are explained by percent urban variable when it enters second into the model. And this is the sum of the squared residuals or errors, right? So the 5,844 that we have there. Now, we can check these residuals by using the resid function, is the way that we can get them or find them in R. So here I'm going to type in UN11A, and I'm going to just use R for residual, and I'm going to have that be equal to RESID m.FLE, and it's going to give me the residuals. So I click that there. And then I could consider calculating those residuals again, kind of by hand, so to speak, in the same way that you had up here. So how would I do that? Well, I'm going to use kind of my residuals is what I'll call it. So I've got UN11A, and I'm going to call this my R. And what I'm going to have here then is I want to have the actual value UN11A, and then what is the variable we're looking at? We're looking at life expectancy for females. And then I'm going to take the difference between that and the fitted value. So where is the fitted value? I'm going to just use the value that we have up here from R, and I'm going to get that's which again, this is very similar to, I could have used my y hat there. It would be very similar. But I'm just going to get this out. So I'm going to click run. So I've got that up there. And now I might want to look at the difference in those residuals. So, right, what is the difference in the residual that's found through R versus the one that's found by actually making the calculation? So I'm going to come down here, and I'm just going to say, I'm just going to create a new variable called diff resid, we'll say, and I'm going to have it be the difference between this, a UN11A, the R variable, which is the residual that R has calculated, and the value that I got, so the my R down here. So put that in there and just run that. So now I've got the difference between these residuals. So then I can look at these. I expect these to be, again, have a total of 0. So I'll just say sum, and then diff resid, and I expect that to be nearly 0. And I get again something here that is very close, right? Point, and then I get 13 zeros, and then 429, so very close. Can also look at the histogram for this. So again, hist for this, and then diff resid. I click run, and again, look over here at the histogram, and they're not all exactly 0. So again, we get some little rounding differences. Some things are a little bit off there, but basically we're getting the difference there as being essentially 0, right? So we can go back over here, and let me go ahead and erase that little thing there. All right, so coming back over here, and I want to check that also the residual should add up to 0. So I'm just going to come over here, say sum, and I'm going to put this residual in here. So get this, copy this out up here, and I expect the residuals to add up to 0. And again, they do, something right, very close. No, it's not exactly 0, but 13, 13 zeros, and then a 5, that's pretty close to 0, so we'll call that 0. And then we can find what the sum of squared residuals is. So the objective of ordinary least squares is it's minimizing the sum of the squared residuals. And so let's go ahead and look at the sum of the squared residuals down here. So I want to look at squared residuals. And so I'm just going to square these here. And I get 5,844.679. You might recall that from up here, 5,844.679, right? That's where that's coming from. Those are the squared residuals. Now, we are arguing that the ordinary least squares method makes that the number the smallest. So let's just come back and grab our coefficients again. We can get the coefficients from our model, sorry. So we've got those there again, and maybe we want to change one of those. Actually, I had them typed up in here earlier, so we can just grab this out here. I'm just gonna pull this in. So we don't really need that exactly. So I'm going to get some different y hats by just changing this. I'm going to just change this to 6. You could change any of these coefficients, right? So the ordinary least squares told us that this number should be 5.32 or -5, and this should be 81 and so on. But let's just change these and see what happens if we just use some alternative values. So I'm just going to call that alt y hat. And so I'm just going to run this. What I'm going to do here is I'm going to now get the residuals, in this case, the sum of the squared residuals for this alternate value. So I'm going to say sum. So I want to add up all of the squared residuals. So what do I have in here? I need to get the squared residuals. So I'm going to take UN11A and get that life expectancy variable. So life expectancy, and the difference from this new value that I just created, this alt y hat. So I'm just going to take that, put that in here. So those are going to be the differences, and then I want to square them and go with that. So now I can get that, and I get this value 7,717, which is more than, so come back up here wherever we wanted to look for it, the 5,844. So that looks right. So I haven't proven that it does give you the minimum, but what I have shown is at least that one alternate value is larger. And you can play with this more. You could type in some different values here for these coefficients and see what that gives you, just to help satisfy your curiosity perhaps. All right, so hopefully what you saw then is that the OLS estimates create the fitted values that minimize the sum of squared residuals. And on average, the residuals are 0. Again, there were some slight rounding differences that you can see that happen out at very small values. But basically, what we're looking at is, the residuals average to be 0. The expected value of the y hats are the y value. So there's our code in Canvas. Go and use it to replicate this demonstration and to check your understanding. Again, that code will have some additional notes in it, or some additional comments. Have a great day.